The boundless and amazing eternal space will always attract our attention. But not only the eternal universe, but also the invention of engineers. In front of you is a perpetual motion machine with the option of a Mendocino engine or continuous operation. It seems simple enough. The light falling on the amazing invention attracts the receivers and changes the mechanism by means of a magnet in motion. Especially in sunny weather, the engine revs up to 3,000 revolutions per minute. Futuristic invention is eye-catching and amazing. I can say that the Mendocino motor is a very unusual and creative gift. It has different variations which can be seen by following the link in the description below the video. And we begin our space journey. All galaxies in the universe, except our own, are very distant astronomical objects. Today, we do not know what happened in this massive gravitational star system. Unfortunately, people shouldn't be there, via teleporter. But this is a doubtful case. Launching an umbrella or other spacecraft is also pointlessly long, since our universes are spread out across the universe and we are separated by great distances. Fortunately, science never stops, and while we can't see these distant galaxies, we can study them from different angles of Earth and its orbit. That's why we suggest you go on a little space trip and find out the answer to the question of what and how the stars are distributed in different galaxies. Each of the galaxies is now going through a different life cycle. They collide, merge with others, develop in their own way, die, and be reborn. And each of them is unique, unusual, and consists of stars of different classes and ages. Everything we know about the universe, stars, planets, moons, and galaxies is found in galaxies. First, we don't know how many galaxies there are in the observable universe. There were once thought to be about 100 billion galaxies. The data was then recalculated, and the number increased to 2 trillion galaxies. At this point, we settled on a few 100 billion. The truth is that looking at the sky, we will not see many galaxies without a special telescope. Only 4 of them. Andromeda, the triangular galaxy in the northern hemisphere, and the large and small Magellanic Clouds in the southern hemisphere. But although we can clearly see the outlines of galaxies in the sky or in photographs, they have no boundaries. It is impossible to say exactly where the galaxy ends and intergalactic space begins. Because if a galaxy is one magnitude in the optical range, then the radius of a galaxy determined from radio observations of interstellar gas may be much larger, and this is not uncommon. Therefore, galaxy size is usually understood as the photometric size of the isophote. An isophote is a line connecting points of equal brightness on an illuminated surface, and its size will depend on the measured mass of the galaxy. But to better understand what we are talking about today, let's touch on the main components that make up the structure of galaxies. Meanwhile, with these talks, we've left the Milky Way, and we can look at it from the outside. Visualize the structure. We are looking towards the galaxy. It is a small region in the center. When we talk about galactic centers, we are often talking about active centers where the processes cannot be explained by the properties of the stars gathered in them. These nuclei contain large amounts of energy-producing processes. The most common signs of active nuclei are a gas jet or high-intensity radio emission. In most cases, the cause of such behavior in the center of the galaxy is a supermassive black hole, including, according to astronomers, the center of the Milky Way. The galactic disk is the relatively thin layer in which most galactic objects reside, a component of disk lenticular and spiral galaxies. This plane has spirals and arms. There is a particularly high density of interstellar gas, and young stars with lifetimes of tens or hundreds of millions of years. They then exploded in a supernova, leaving behind a core and core of ejected matter. In the most massive stars, it collapses and becomes a black hole, while in low-mass stars, it becomes a neutron star. So the galaxy has plenty of building material to form new stars. There are many stars known as cradle stars, where some stars die, and then other stars are born. One example of such a cradle is the famous Orion Nebula, or M42. You can see it visually as an eerie spot in the clear black sky on Orion's sword. In a telescope, you can see the structure of the dome and individual stars. The images clearly show a dome illuminated by the bright stars of Orion's trapezium, a young, diffuse star cluster located within the dome. You can find the constellation Rigel without taking your eyes off the constellation Orion. It is a blue-white spherical giant and contains stars similar to ours and many other spiral galaxies. Rigel, like other stars in this class, lives for only a few million years and then explodes, leaving a lot of building material in space for new stars to be born. These clouds are scattered star clusters. They are so called because individual stars can be easily distinguished. In the Pleiades and Hyades, for example, stars can be seen with the naked eye. They are sometimes called galaxy clusters because they are located in dusty spiral arms. Stars in an open cluster have a common origin, that is, they formed from the same initial molecular cloud. A cluster usually contains a few hundred stars, which can reach several thousand. The stars are bound by gravity, but it is very weak. Clusters orbit the galaxy and are dispersed by gravitational contact with more powerful objects in the final phase. By the way, our Sun also formed in an open cluster, which no longer exists. So they are always young things. The region is still visible on the WIP, indicating the final formation. The galactic disk, as you can see, is denser than the surrounding spherical component. For example, corona or halo, where old stars lived. So we gradually moved on to the next galactic structure, the galactic halo. This invisible spherical component is hypothetical, which means that it already deserves external attention. By studying the halo, one can understand where the gravitational influence of one galaxy ends and another begins. As for the stellar composition of halos, they are typically old stars in the form of red and brown dwarfs with their systems and worlds. There is not a single red dwarf in the universe that ended its existence after the Big Bang. Red dwarfs are small stars after brown dwarfs. These objects have enough mass to initiate thermometric reactions, but due to their size, these stars are slow to emit light. Sometimes jokingly greedy and generous dolls were not found. Sometimes these stars emit light tens of thousands of times smaller than the Sun, making them invisible to the naked eye. They are relatively faint, but they are the longest-lived stars in the universe. We often hear the advice to be excited and not waste our energy, and red dolls are an example of this. They will live for another tens of trillions of years and slowly die peacefully. Death is slow and almost imperceptible without pain. The maximum temperature of red bushes is 3,500 degrees. Power doll is really bad. Not a planet or star. These dolls are heated to a maximum of 2,300 degrees Celsius. But because they cannot maintain internal thermodynamic reactions, they are in danger of cooling down for a long time and disappearing. In a few 100 million years they will cool down, cease to emit their feeble rays, and become lonely and unrepentant cold wanderers in the wicked expanse of space. Some astronomers believe that the brown dwarfs are stars, while others believe that they are giant planets and call them hot Jupiters. On the one hand, such an object, like a star, will live until it emits the remaining light and the faint heat in the light. In contrast, a brown doll will live relatively forever, for example, until it is captured by a black hole. The globular gravitational system also contains globular clusters of between 2.5 billion stars. They also feature the most famous stars. Clusters are so old that any star has passed the main sequence. A globular cluster has little dust and gas, because no new stars are formed there. The density in the inner regions is much higher than in the areas near the Sun. Stars in globular clusters also share a common origin. But this type is held tightly by gravity because stars are not expanding, unlike non-expanding clusters. For reference, there are about 200 globular clusters in the Milky Way. The next galactic component is the rare polar ring. For example, the galaxy in front of you is NGC 4650A, and it has such a component. In the classical case, a polar ring galaxy has two disks rotating in a perpendicular plane. For scientists, the reason for the formation of polar rings is still a mystery. Polar ring galaxies are a type of galaxy in which the outer rings and stars orbit the poles, and these polar rings are thought to form when two galaxies interact with each other gravitationally. The next galactic component is bulge, the central, bright, ellipsoidal component of spiral and lenticular galaxies. It consists mostly of old stars traveling in long orbits. Typical populations of galaxies are red giants, red dwarfs, or Type II supernovae, as well as variable stars such as Lyra. There are also the globular clusters discussed earlier. In typical lenticular galaxies, it is larger than the diameter of the galaxy, such as in spiral galaxies. We're a little tired, so we can talk about the bar. No, it's not a bar. It's a galactic streak, or in layman's terms, a leap. It resembles a dense column of stars and interstellar gas, and is the main source of interstellar gas to the galactic center. Now that we know the necessary components, we can move on to the classification of galaxies and learn more about these star islands. For example, the elliptical galaxy makes up about 25% of the total number of high-luminosity galaxies known to us. From the outside, it looks like a giant star, with a bright center and a shiny edge. Elliptical or spheroidal galaxies consist almost entirely of old stars, so they are always yellow or red in color. Surprisingly, they do not form new stars because there is little interstellar gas and dust. The best-known representative of this type of galaxy is M87, a supergiant elliptical galaxy in the constellation Virgo. Mathematical model programs based on the principle of organization and operation of biological neural networks are nothing but artificial neural networks. The structure of neural networks came directly from biology to the world of programming when researchers began trying to model the processes that occur in the brain. Thanks to this structure, the machine has the ability to analyze, recall, and repeat from memory. In the middle of the 20th century, the first steps towards artificial intelligence and cybernetics began to be made. Mathematicians, neurophysiologists, neurolinguists, and others have studied how machines can use concepts of logic and abstraction in the process of self-learning and self-improvement. Today, artificial neural networks are widely used in economics, finance, and chemoinformatics to predict the properties and biological activity of chemical compounds needed for drug development. It can also recognize face and speech, use different masks in applications, process our favorite photos and images, right through voice and game industry. All this is easily overcome without using neural networks. In recent years, many researchers have begun to notice that there is an unusual connection between multi-layered neural networks and not only the human brain, but the entire universe. By the way, a neural network can be single-layer or multi-layer. Generally, any neural network consists of two main layers, a signal-receiving layer and a processing layer. However, if a neural network consists of only these two layers, it is a single-layer network. If multi-layered, multi-layered, and it will have better performance and capabilities than single-layer. In fact, in just the past 2 years, deep learning techniques have revolutionized the world of artificial intelligence. One by one, The abilities and techniques that people considered unique began to fall under the onslaught of powerful machines. Deep and multi-layered neural networks are now better than humans at performing a variety of tasks. But there is one unresolved conundrum. Mathematically, programmers cannot determine why networks organized in layers should perform well at these tasks. That is, despite the great success of multi-layer neural networks, no one knows exactly how they achieved such success. Skynet. Don't jump to conclusions. The reason programmers are confused is that the answer is believed to depend on the nature of the universe. In other words, the answer lies in physics, not mathematics. First, let's take the example of classifying a megabit grayscale image to determine whether it depicts Chewbacca or Citripe. Such an image consists of 1,000,000 pixels, each of which can take on one of 256 gray values. So, theoretically, there could be 2,561,000,000 images, and each of them needs to depict a certain creature. Neural networks with thousands or millions of parameters somehow do such things easily. To put it mathematically, neural networks simplify complex mathematical functions approximately. For ease of understanding, approximation is a computational method in which complex objects are replaced by simpler, but as similar as possible, computational objects. When it comes to image classification, a neural network must implement the input function of millions of gray pixels and obtains the probability distribution of the item it represents. Again, the problem is that mathematical functions are orders of magnitude larger than they approximate as networks. But deep neural networks somehow get the right answer. The universe can be governed by a small subset of all possible functions. In other words, when the laws of physics are written mathematically, they can all be described by functions with simple sets of properties. Thus, deep neural networks should not approximate a possible mathematical function, but only a small subset of them. Yes, the laws of physics have other important features. For example, they are symmetrical when it comes to rotation and movement. Turn Mr. Freeman's statue 360 degrees, and it's the same. Move it 10 meters, or 100 meters, or kilometers, and it will look the same. That is, it simplifies the problem of approximating the pattern recognition process. This characteristic means that neural networks do not have to approximate an infinite number of possible mathematical functions, but only a small subset of the simplest ones. There is another feature of the universe that neural networks use. This is a hierarchy of structure. Simply put, these are the particles of an element that make up an atom. In turn, they are molecules, cells, organisms, planets, solar systems, galaxies, etc. For example, let's take the cosmic microwave background radiation, the sound of the Big Bang that permeates the universe. In recent years, various spacecraft have produced this radiation with even higher resolution. But the question here is why the cards take this form. Whatever the cause, it is undoubtedly the result of a hierarchy of causes. Every event has a cause, and at the same time another event has a cause, or vice versa. Indeed, nothing can exist without a cause, not even an ocean. Thus, a set of cosmological parameters, dark matter density, etc., determines the spectrum of density fluctuations in our universe, which in turn determines the cosmic microwave background radiation, reaching us from the first universe. Each of these causal layers of a neural network contains more information. There are only cosmological parameters, but the maps and the noise in them are made up of billions of numbers. The purpose of physics is to analyze large numbers to identify smaller ones. And when a phenomenon has such a hierarchical structure, a neural network greatly simplifies the process of analyzing it. Artificial neural networks are based on biological networks, so that explains why deep learning machines do so well. It also explains why the human brain can understand the universe. This knowledge is making great strides in artificial intelligence. Now that we understand why multilayer neural networks work, we begin to learn the mathematical properties that allow them to do so well. Subsequently, the training of complex multilayer neural networks has produced great results in recent years, and they have been widely used in various fields of science, including astronomy. Today's space explorers have such advanced observation tools that they don't have time to study the images they capture. Today, automated observatories collect vast amounts of data, more than was collected in the entire history of astronomy before the beginning of the 21st century. In addition, a completely new method of studying cosmology using artificial neural networks is used. For example, cosmologists usually determine the composition of the universe using long-term observations. But these days, a machine learning algorithm can only examine a single model galaxy and predicting the total composition of the existing digital universe. That is, a neural network that learns a single grain of sand in the Sahara Desert can predict the entire mass of the network, such as a question consisting of a few dozen words separated by commas. Sounds like science fiction. But the machines seem to have found a pattern that allows astronomers to draw radical conclusions about real space by studying its basic building blocks. This means that instead of measuring and studying a large number of galaxies, it is enough to take just one to predict the composition of the universe as a whole. But these are not just words. Cars do it. The remarkable discovery turned into a major project in which, knowing the properties of the galaxy, many cosmological features can be estimated. Finally, the computer calculated the total density of matter. Next, the researchers analyzed 2,000 numerical universes created by the Cosmology and Astrophysics Project with machine learning simulations. The composition of these universes varies from 10% to 50%, with the rest coming from dark energy, which has anti-gravitational properties and is involved in the expansion of the universe. If you recall the theory, about 5% of our universe consists of visible matter, stars, planets, galaxies, and gas. 25% dark matter and 70% dark energy. When the simulation was run, dark matter and visible matter were added to the galaxy. The modeling also includes a rough treatment of complex phenomena, such as supernovae and jet-shaped supermassive black hole emissions. The neural network studied nearly 1 million simulated galaxies in these different digital universes. Their size, composition, mass of each galaxy, and more than a dozen other properties. Tested in thousands of new galaxies from dozens of digital universes. Neural networks have not been investigated before. He was able to predict the density of cosmic matter with an accuracy of 10%. It doesn't matter which galaxy the neural network learns. The algorithm's performance surprised researchers because galaxies are chaotic objects. There is a large classification of galaxies of different types and sizes. Some appear all at once, while others grow without eating their neighbors. Giant galaxies persist, while supernovae and black holes in dwarf galaxies can eject most of the visible matter. The vastness of our universe has never been considered. Its age and size are unfathomable. Our planet, with the people on board, lost somewhere in space. They, in turn, are well developed and have recently produced interesting and noteworthy theories about the origin and structure of the universe. The Big Bang Theory is widely accepted as a cosmological model of the Earth orbiting the Sun. According to the theory, about 14 billion years ago, spontaneous expansion in an absolute vacuum created the universe. Something of this magnitude is unimaginable in a fraction of a second. But there are many flaws in this theory, and many physicists, scientists, and fictionists are putting forward new predictions. Here are some of them. Stationary universe theory. The universe is always in an unchanging state. Proponents of the stationary universe theory popular in the 1950s and 1960s, believed this. What about the apparent expansion of the universe? Proponents of this theory believe that the universe may be expanding, but that it remains the same, that matter is constantly being created and nothing is being created. Cycle model. This theory does not disprove the Big Bang theory, but it does confirm that there were successive Big Bangs. Between the two big explosions, there was a big explosion. So the universe expanded to a limit, and then contracted. A big leap. This interesting alternative theory for the Big Bang suggests that there was another universe before our universe. So, while the birth of the universe, or the Big Bang, appears to be a unique event, in this theory, it is just one link in a chain of reactions that the universe repeats over and over again. Line theory and M theory. It also has many generations, but the general idea is that the universe can always repeat itself. Some believe that our universe was formed as a result of quantum changes in an earlier universe. So at some point, our universe may undergo new changes for some reason, and a new and different universe may still exist. Emergence. For example, did you wear pink tights today? So maybe there's an alternate universe where you don't have a doppelganger next to you for ethical reasons. While we're on the subject of illusions, there's another theory that says we're all in a hologram created by the universe itself. According to this theory, if we look at the night sky, we see a wall covered with the image of all the galaxies and stars. Which theory do you think is reasonable? Let's figure it out together. First, let's go back to the time when the Renaissance scientist Nicolaus Copernicus did not consider the Earth to be the center of the solar system. People understand our planet in a new way. His idea was one of the greatest scientific discoveries of the last few hundred years, and is an important place in understanding the inner structure of the cosmos and the nature of the real world. We know that our planet orbits an average-sized star, one of the 200 billion stars in the massive body that make up the Milky Way galaxy. Our galaxy is one of hundreds of billions of similar structures in the observable universe. By human standards, the universe is a lot of matter and a big place. Imagine that you have traveled to one of the distant galaxies and are about to send a monkey to your loved ones on planet Earth. So, the third planet from the Sun. Next is the solar system in Orion's arm, around the Milky Way. Then you will see the Milky Way in the local group of galaxies. A nearby cluster of more than 50 galaxies is spread over about 7 million light-years. The local group is located on the outskirts of the Virgo cluster, home to more than 1 billion galaxies, 50 million light-years away. This cluster itself is a small part of the local supercluster of galaxies. It unites hundreds of similar clusters spread over 100 million light-years. Superclusters are the largest structures in the known universe. They consist of groups similar to our local cluster, containing tens of galaxies, as well as massive clusters containing hundreds of galaxies. All these clusters are connected, and the boundaries are not easy to define. Let's hope the monkey doesn't see any other civilizations heading towards Earth. In addition, the entire system is expanding, separating the galaxies even further, and points on the surface of the sphere seem to be moving further apart. It has created a catalog of cosmic currents of such unimaginable size that it contains a wealth of data that sheds light on the dynamics of 1.8 thousand galaxies within 130 million light-years of the Milky Way, and 8,000 galaxies within a globular globule with a radius of 650 million light-years. As the catalog grew, they suddenly discovered a picture hidden in the mass of data, new, never-before-seen examples of cosmic construction. A cluster of galaxies spanning more than 400 million light-years is heading towards a tiny gravitational field, like streams of water joining the lowest point of the landscape. If the universe had no mechanism, these galaxies would eventually merge into a single compact structure bound together by gravity. This large collection of galaxies is called the Laniakea supergroup, which is Hawaii for brain melting. Okay, just kidding. Big sky. For the early Polynesians, they navigated the vast expanses of the Pacific Ocean with the stars. A ruler is not just another line of our space address. Its diameter is 500 million snakes. It consists of 100,000 galaxies with a mass of about 100 million billion solar masses. Superclusters also include the Virgo cluster and the Great Tractor, or Puller. The movement of galaxies within the Laniakea supergroup is like water flowing through a valley. The Great Gravitational, in turn, acts as a large, flat-bottomed gravity valley with an active region in the shape of the Laniakea supercollapse. By studying the architecture and dynamics of this giant structure, we can learn more about the past and future of the universe. Mapping the galaxies that populate it and studying their behavior can help us better understand how the mechanisms that drive galaxy growth and motion are formed, and will also reveal new details about the nature of dark matter, the invisible matter that makes up 80% of the universe. Of course, everything in the universe is relative. The world we live in can seem unbelievably large. It is a small part of a larger structure, the solar system, which in turn looks like a small grain of sand against the background of our own Milky Way galaxy. These distances are so vague, in comparison, it's like throwing a sandbag on a football field. So you only get one particle that is the solar system. Humanity is making scientific discoveries day by day. It's like a moment of epiphany that shatters our worldview. For example, this happened when we learned that the Earth was uneven. Our planet revolves around the Sun, not the other way around. There are other galaxies in the universe. This process continues. With each step, our knowledge expands, and the next scientific discovery leaves new questions.